Today we start capsule number 2 of this course, which will have two presentations, two lectures. The first one today will be on essentials of incompressible flow, and the next one would be on three important concepts: the Bernoulli's and Coanda effect and Mach number. So this constitutes part 1 of the basic aerodynamics. This particular presentation was prepared by Tanmay Heblekar from MIT Manipal. As I mentioned, he is the one who spent 2 months in this summer working for us. Let's have a look. I just want to first give you a basic heads up on what all we will cover. We are going to cover only very basic things, and it would be limited to fluids, and also we will look only at kinematics of fluids. Okay. So we cover this topic in three bits. The first is we look at the difference between the approaches, two different approaches which are named after two scientists, Euler and Lagrange. We also look at a concept of material derivative or substantial derivative, and we see how it can be applied to basic fluid kinematics. And finally, we will define and understand the concept of steady and uniform flow by demonstrating unsteady flow and its features also. So these three are what I plan to cover today. Okay. So what do you see in this figure? What do you see? Yes. Right. So the question I want to ask is, what do you see in this? So one gentleman said he sees randomness. Okay. I think there is some order also. Many of these vehicles are in the same line. Anybody else can add and explain what do you see? Yes?
Heavy traffic.
You see heavy traffic. Okay. But is the traffic moving? No. Okay. So let us assume that these vehicles, so they are not moving because the red lights are on, those are the brake lights. But if we assume that this is a multitude of moving cars, okay, let us imagine that each vehicle becomes a fluid particle. As you can see, there are different sizes, different, similar but different shapes, okay. And let us focus our attention on only one of these vehicles. Just on one of these mass vehicles, we focus our attention. We zoom close into it, and what do we see? We see there is a single car, okay. But here, fortunately or unfortunately, there are no neighbors here, but we have removed the neighbors and we are focusing on this particular car. So if you focus on one such vehicle in a moving traffic, this approach is called as a Lagrangian approach. When your attention is focused on a particle that is moving, that is called as a Lagrangian approach. Okay. How do you, okay, I will talk about it later. So literally identifying and tracking a specific fluid element. Okay. Now this is an obvious notion in the mechanics of solids, because in your basic classes, whether when you were undergraduate or whether in the previous courses, you must have seen that this is the kind of notion which is very obvious in solid mechanics. The properties of this fluid element, they are a function of time. They are not constant, they need not be constant. We assume that they are a function of time. Okay. You cannot say function of space because it is moving. So the space is moving along with it. The space around it is not a constant. So therefore the properties are only a function of time. Okay. So the position of the particle is a vector because it has a magnitude and direction, magnitude in the sense of the coordinate frame, and direction. So it is a position vector. Then we have the velocity of the particle as a function of time t, that would be the derivative of this position over time. Remember, it will not remain the same depending on the signal, depending on the traffic, depending on what is possible, the velocity will change as a function of time. And the acceleration also will be in general a variable which is a derivative of its velocity over time. So this is the Lagrangian approach. Now let us see another example of a Lagrangian approach. Assume that we have these helium filled balloons which are carrying a small payload. The payload could be a probe or a sensor which measures some property. It could be, for example, humidity or temperature or pressure, any parameter. So now what happens to this particle is that as a function of time it is moving, okay. So where is our attention focused? The attention is focused in this example on the specific object that is moving in space. So therefore this probe which measures any property, it is making Lagrangian measurements. It is measuring a property over a function of time. Okay, right. So now let us look at, on the other hand, let us say you have a traffic policeman and now you are standing at one point, okay, and you only observe what is happening at that specific point over a period of time. Such an approach would be called as the Eulerian description of, or the Eulerian approach. Okay, so let us understand. In an Eulerian approach, our attention is focused on a particular place. For example, the main gate, just outside the main gate, you are focusing only there, and then you see a stream of cars, vehicles passing by. Now this particular approach has more mathematical implications. The previous one had more physical implications, because that is what we studied in school, etc. We say two cars are moving, etc., etc. They were all Lagrangian approaches. This one is more mathematical, okay, because the properties in this approach are expressed as field functions of space and time. Space because it is a fixed location, time because over a time the properties or that particle are observed. They may be fixed, they may be changing. With this I want to ask one basic fundamental question: when is a function defined as a field function? There is a mention here of a field function. So before you answer, remember our two rules. One is to raise your hands and second is to grab a mic before you answer if you are chosen to answer. So who will help me define field function? Yes. Perfect, very good. If there is a function and that function is defined everywhere in the space, there is no region in the field or space where it is undefined. There are no holes in the domain. Okay. Its value may be the same, it may be variable, we don't care, but it is defined. So if the function is determinable at any arbitrary point in the field, we call it as a field function. Most physical phenomena, tend to be field functions. Okay. So therefore it is easy for us to say, okay, at any point you can define it. So then look at, for example, the velocity field. The velocity field can be written as a velocity v, which is a vector, which is a function of the location in the Cartesian coordinates x, y, z, and time. So it can vary as x varies or y varies or z varies or t varies or any of these vary. Correct? That is a velocity field. So an example, this is a typical drawing room. You have a fixed point in space P. At that point I install a thermometer. So the thermometer that is fixed in space is going to measure only Eulerian measurements. If I record the reading of this thermometer over a day, I can get the value of temperature at that point x, y, z as a function of time. Typically it will increase, then become less, etc., etc. Okay. So the T of the thermometer, which is the field function, everywhere it is defined along this field. Is there a place where it is not defined? It is defined everywhere. It's a function of the x, y and z coordinates of that point P and time t. Okay. So, since we don't have a blackboard, I thought we will use blackboard as an example. Okay. Let's understand the Eulerian approach physically. So, let's assume that for a particular scenario, you define the velocity at the point 3, 1, 5 in space at time t equal to 3.5 units. It could be hours, seconds or milliseconds or nanoseconds. Let's define this velocity as 2I plus 9j plus 7k. So, it's a vectorial representation in terms of ijk. What can we infer from this? In fact, what we can infer, I have already told you. So, at time t equal to 3.5, the particle is present at 3, 1, 5. It is present and the velocity is 2I plus 9j plus 7k units. That's all we can infer. Can we make some other inference also? Apart from these three important inferences, is it possible to make any other inference if we give v, x, y, whatever? No, I don't think anything else can be concluded. So now we have these two scientists fighting for our attention. We need to understand the difference between their approaches and why both of them are useful and important for us when we study fluid mechanics. So often people get confused and they get forgetful. So when you have your quiz for capsule 2, if there is a question about Eulerian approach, you will say, "Kaun tha yaar Euler? Was he the policeman or was he the car moving in the traffic?" So how will you remember? To remember certain things which are very confusing and similar, you need to use imagination, or you need to tell yourself some interesting way of remembering. So I'll share with you how I remember. I know that one of them concerns moving, the other concerns fix. So this Lagrangian has a word range inside, and the range for me brings, in an aircraft the range means moving from A to B. So I remember Lagrangian as moving, and hence Euler is a policeman. That's how I remember it. Okay. You can have your own mnemonics, your own way of remembering. So basically, these two are connected. We can easily connect them, and one way of connecting them is called as the Reynolds transport theorem, but we will not study that today. We will use the other one called as the concept of material derivative. Okay. So once again, you can understand the connect between these two scientists and their approaches using two methods. There could be more, but today we will discuss only the concept of material or substantial derivative to see how these two are connected. So let's see. If I ask once again, what do you see? There is a place which is having some fire. So when you see fire, which property do you get along with it? Wherever there is fire, there is temperature is everywhere. Even in this room there is a temperature, but we are not on fire. You can say high temperature, heat, which causes temperature. Okay. And the other thing is an ice cream. Which property? Don't say that mango delight or tutti frutti or peppermint when you say property. I'm not talking about that property. What property or what thermodynamic property do you immediately get in your mind when you look at an ice cream? Again temperature, but low temperature. So from hot to cold, it's a temperature field. So let's see, this is a field, and we have used this color scheme to indicate the temperatures. So blue being cold, red being hot, so there is a temperature gradient. The temperature is reducing as per some particular law, which need not be linear, but there is some way it is reducing. So there is one place at which the temperature is T is equal to T hot. T hot is a number, it could be 512 degree Kelvin. Okay, and then there is another temperature T equal to T cold. So in this particular field, from a hot place to a cold place, in this field temperature varies. Now let's look at one bumblebee. Now why have I chosen bumblebee as an example? Because as per the basic laws of aerodynamics, a bumblebee cannot fly, but a bumblebee flies. Okay, so that's why it's interesting that if you look at the basic description of aerodynamic forces, then a bumblebee should not be able to fly. But bumblebee doesn't believe in Lagrange or Euler, it flies. Okay, so there is a bumblebee which flies. It flies from this particular place X, which is called as X fire, to X ice. So two locations in space in which a bumblebee is flying, and what we do is on the bumblebee we put a small temperature sensor, and because it's difficult to read that particular scale, bumblebee is small, the scale has to be also very small and lightweight, so I have just taken a projection in the center. So as the bumblebee moves, you will see the arrow moving in that particular temperature scale. So as it moves from there, as a function of time, the temperature recorded by the sensor mounted on the bumblebee is slowly recording a reduction. Here we assume that this sensor is having an instantaneous capability, that within few nanoseconds it is able to measure and display the temperature that is actually prevalent. In real life it will take time. Typically if you put a thermometer on a bumblebee, by the time it reaches, it will still show high temperature because there is some soaking time needed. But let's ignore those practicalities here. So the bumblebee experiences a temperature from T hot to T cold, varying at a particular rate when it goes from a place X fire to X ice. So let's now look at some basic observations. Since we are now focusing along a line, okay, remember the sensor is mounted on the bumblebee, but the bumblebee is moving. Therefore the recordings or the approach for Mr. Fly is basically a Lagrangian approach. Then the temperature changed simply because of its motion and change in location. Okay. So it's a property which is a function of its location. Obviously the rate at which temperature changed was not necessarily a constant. In our example, probably you must have seen it is a linear change, but it need not be so, we don't know. And also the numerical value of that rate can also be altered. If the fly moves at a very fast speed, the rate will be different from when it moves very slowly. Secondly, the field may have certain elements which are sucking or expanding heat, therefore the temperature gradient, if it changes, the rate of temperature change also will change. So there are certain properties of the field which affect the rate of change of temperature. One of them is the speed, the other one is the gradient. So now we have seen an example and we have to now put this down mathematically, because something like this happens to a fluid particle also when it moves in a field. So let's see how to do it mathematically. Okay. So what we say is that the rate, time rate of change of this property called temperature, and here temperature is a scalar, it's just one particular parameter, that is equal to the rate of change of the temperature gradient as you go from this place to this place, plus the velocity. Okay. So the temperature change as a function of time will depend on both the things. The velocity of the fly, so suppose velocity of the fly is 0 and the fly remains at that particular place. So do you think if you are standing over fire and there is an ice cream somewhere nearby and that ice cream is now melting as a function of time, the temperature will not remain same. Okay. So there will be a change in the temperature by virtue of time also. There will be a change in temperature by virtue of speed also. So both have to be considered if you want to get the complete and total change of temperature as a function of time. So now so after some time the ice cream starts melting. That means there is some heat transfer happening. So the temperature at every point, and the ice cream melting will not only locally change the temperature, but maybe less or more, but everywhere there will be a change in the temperature. It could be very less, very far away, but there will be a change. So at every point in the space now, the temperature becomes a function of time. Okay. So T is a function now of x, the location of the fly, and T, the time at which the recordings are being made. Back to the green board. So temperature T is a function of location and time. So there is something called as the total derivative theorem, which says that if a parameter such as T depends on two parameters, then if you want to find out the total derivative of that particular property or that particular item, which is capital T, you can take it as the partial derivative of that with the first parameter, that is x, the distance, and then x with T, and then you have to add the partial derivative of that property with time into dt by dt. So this is called as a total derivative theorem. This is true for any property such as temperature, which depends on more than one parameter. Okay. So now ultimately what will happen is, so total derivative of temperature with time would become partial derivative of temperature with x into velocity, because v is dx by dt, change in velocity, plus partial derivative of t upon time, with time, and that's all. So the total derivative will be a sum of two partial derivatives. Okay. Any questions anybody has? You can interrupt in between. It's actually fairly straightforward. But if this is true, then you must tell me under what conditions is this exactly true. If you have understood this derivation, then you should also tell me this is not universally true. The way it has been written is not universally true. So for which condition is this true? Yeah.
Sir, it must be an isolated system. That is, no heat exchanges with the
fine. So it's a system which does not exchange any heat from outside to inside. Yes, that is acceptable, because otherwise there will be a effect of the outside temperature on the temperature variation inside. Other than that, any other constraint? The way it is expressed is true only in a particular condition. It is yes, which means one dimensional flow. Correct. Equation 1 is valid only for a one dimensional situation when there is no variation with y and z. Okay. So now let us open it up from a flat blackboard, make it a 3D room and allow variation with x, y, z and t, which is what we started with. So for 3-dimensional cases, it will become partial derivative of t with time, which doesn't change. But now v will become the v vector dot delta t, del t. Okay. So where del t will be partial derivative of t with x into I plus t with y into j plus t with z into k. So extending the dimensions, it becomes partial derivative of temperature with time plus v dot del t. Okay. So now I replace the word t, capital T, with some small function, any function f. For any field function, the total derivative of that function with time would be its partial derivative with time plus v dot del f. So what are some interesting observations here? What is this? What will you call this point number 1? What would you name it? Yeah.
Total derivative.
This is the material or the Lagrangian derivative or total derivative. There are many names for it. So because it's called as a material derivative or a Lagrangian derivative, it's a name. Okay. what would be this? Local derivative or the Eulerian derivative. So local means policeman, that's Eulerian. Total or complete is Lagrangian. So we are now saying, so Lagrange is more than Euler always, not always, in some cases when del dot V dot del F is 0 then they will be the same. So now the last one is very clear. So the middle row, what would you think is number 3? What do you call this term? Yes. Space derivative. Where is the space coming there? No, it's a transport derivative. Okay. Or convective, because it is because of moving. So the total derivative is equal to a local derivative plus a transport derivative or a convective derivative. This is how we will define basic fluid flow. So yes.
So if we take f as any function, any field function,
Yes.
then what is v?
V is a property which is associated with that field function of the fluid particle. It could be viscosity, if you are looking at viscosity changes. In this case, we have looked at changes in the distance or location. So in general, the third term depends upon the convection or the transport of some phenomena, some what shall I say, some parameter in that particular field. Okay. Remember, it could be 0 also. So that's where how we will define steady flow, etc. Okay.
It's not necessary that v should be velocity.
No, it's not necessary to be only velocity. It's this example. Okay. But in most fluid particles, it's only velocity. But if you look at magnetohydrodynamic modeling of flow, it may be some other particle. But when you have something moving, some particle moving in a flow field, then it is velocity only. So in general, you can say it's some convective property, some property because of which there are changes happening over a function of time, which is velocity in most cases for fluid particles. Good, I really like these interruptions. These interruptions are helpful in clarifying even to me how I can add more information in this presentation for future batches. Alright, so this is the material derivative. What it tells us is how quickly this field function f changes for the moving element. So this is the total story. The partial derivative or the local derivative, Eulerian derivative, it tells you at a particular place what is happening, because it is a function of only time at a particular pace. And the convective derivative tells you by virtue of the element's motion, in this case by virtue of motion, how f is changing. There could be some other class in which we are talking about some other, not fluid mechanics but some other mechanics, and there the same equation might represent not motion but something else. Okay. So whenever there is motion related changes, velocity will come into picture. So the definition is very general. So now we are fully armed. We have all the required mathematical support to proceed ahead with the definition of, remember what is the whole purpose of this exercise? To define what is meant by incompressible flow. That is our chapter. We are here to look at incompressible flow and to define what it is. Okay, now when we come to this point, I am reminded this is a very interesting aircraft and it is fully armed, as you can see. So just a small deviation. Can someone tell me what is this aircraft? Name the aircraft first. Yes. Yes, it is the A-10 Warthog. So do you know any special features about this aircraft? Okay. Which is there right in the front, there is a gun. Okay. Yes. Not only US Air Force, but yeah, yes, ground attack. So it's an anti-tank basically an anti-tank aircraft, an aircraft designed for attacking the ground forces, right? What else? Right. Exactly, I was going to say that, very right. It is essentially an aircraft built around this cannon, air to ground cannon right in the nose. Yes, and there are many other interesting features. Okay, so I am trying to now sell myself. If you ever attend a course in aircraft design that I would teach in the future, I'll talk about this aircraft in great detail, because this is one of the very good examples of how you can design an aircraft for combat survivability. So we are fully armed, we have A10 with us. Let's go ahead and ask some questions to understand. This will tell me rather, and also you yourself, how much do you know. So the question is, what is incompressible flow? Is it a flow in which density remains constant? Is it the flow in which the rate of change of density with time remains is zero? Or is it when the fluid involved is incompressible? In which situations can we term the flow as incompressible flow? So now, just like the quiz, all three may be wrong, all three may be right, two may be wrong, etc., etc. So let's see if you can answer this question. When do we define a flow as incompressible flow? So how many of you feel that the flow is incompressible when density is constant? Yeah, we have one hand raised there.
My name is Anando,
Yeah.
and when some pressure is applied on the fluid, if the change in density is insignificant, I mean less than 10% or something, so we can call that fluid incompressible.
That means using partial derivative of rho by partial derivative of time is equal to 0. That is the answer you are giving?
Reality.
That's
No,
what you said, no?
it won't be 0. It will be close to 0.
Almost 0.
Almost 0.
Okay, when it is almost 0, fine. That is his point of view. Yes, we have another person here. Name please.
My name is Rahul.
Rahul, okay.
And so we call a flow as incompressible when the density does not change with respect to the space as well as with time.
So density equal to constant with respect to space and time.
Yes.
Then it is incompressible. Okay, that means the first choice. Density is constant. Any other? Anybody else would like to add to this? Yes.
I'm Kavita. I think the density incompressible flow is the one in which there is a change in density, but it is less than 5%.
So you are again corroborating what he said, that there is a change in density but very small.
Very small.
That is when you call the flow as incompressible flow.
Yes.
Okay. This is what we have all come up to believe so far. So I want to trash that myth. Let us see what is the, not exactly, that's not exactly the truth statement. Let's see. Basically, it should be the total derivative to be 0. So that's where you stand corrected. It is not just density remains within 5%. All these answers are true only for one dimensional flow or for steady flow or for, yeah. So basically, if you say in a steady flow, then I understand your points are correct. But the correct definition is that the total derivative, the substantial derivative, the material derivative, whatever you like, of density with time should be 0. Only then the flow is actually incompressible flow.